at the University of Urbana-Champaign. So I've been there for a long time when I was a PhD student. A little bit cold, but a very nice place. And this work with WebMayhew, PyLog. I'm not so familiar with the work, so that's why I'm very interested and to know what's happening here. And he was saying that if we have any questions, we should stop him during the questions. Thank you for volunteering for the talk.
Yeah. Thanks a lot. Thanks a lot, Professor Reno, for the introduction. And indeed, here these days we have very cold weather these days. It's like it's like below 5 degrees at this point. And thanks a lot for the invitation. And today I'm very happy to discuss with you one of our recent project. It's called PyLog, and it's an algorithm-centric Python-based FPGA programming synthesis flow. So I'll talk in detail about the project. And yeah, so feel free to interrupt me if you have any question anytime. So I'm happy to discuss all the questions. So just to start with, let's talk about the background, the big picture of this work. So basically, we've been seeing new challenges in modern computing. So those challenges, I would say, first of all, complexity in data. So the complexity has many different aspects. So in terms of data volume, in terms of the dimension of the data, in terms of the formats of the data. So there are a huge number of data and in different complicated formats. Also, complexity in applications. There are many different application scenarios in cloud, at edge, and so on. Also, complexity in hardware. So there are very diverse range of hardwares. But if we compare the complexity of data, or more specifically, the growth speed of data against the performance growth of processors, we can see there's a huge difference. So this is basically telling us that we need a very efficient hardware accelerators. Also, if we compare the growth of application or algorithms against the growth of processors in terms of manufacture process, or more concrete, Moore's law, and we can see still there's a huge gap. So this picture is an interesting graph that compares the number of machine learning papers published every day and number and Moore's law. So you can see it's very hard by pushing the manufacturer process processor to catch up the speed of new algorithms being proposed. So that tells us basically we need a rapid design flow. So basically my research or more generally the projects happening here in our group has been focusing on those areas, designing highly efficient accelerators and rapid design flows to create those accelerator systems. And a very high level overview of my research projects for the past few years. So at the very beginning, people introduced several kinds of hardware accelerators to help CPU to process deal with different kind of applications. So the accelerators include GPU, for example, include FPGA. So we've done some work in this domain, targeting those data mining, bioinformatics applications. And later on, people start to put those accelerators and general purpose processors together, and we get SoC systems. So those SoC systems will have a lower power, but they still have a very good capabilities in processing. We use them to do low power, but real-time object detection, for example. We use them to do sparse DNA inference and so on. So we have done some work on that space. And at the same time, people introduce more advanced hardware features into those SoC systems. So for example, shared virtual memory, system-wide atomics, and so on. And so improve the efficiency of the system will become a challenge. So we did some work to enable the tighter collaboration between CPU and accelerators and optimize for the overall system performance. Also, at the same time, there are emerging hardware architectures that comes to into the application domain. So that are, for example, ReRAM-based accelerators, or more generally, concept of processing in memory. So they have a unique characteristics that make them pretty powerful in processing certain applications. So I say overall loads are hardware platforms, and we have many advanced features for those hardware platforms. We have very efficient hardware accelerators. But the next question would be, there are more and more new applications in many different domains with many different application scenarios. So the question will become, how can we efficiently map those high-level applications onto our advanced, sophisticated hardware accelerators? So to solve this challenge, the critical part will be the compiler and programming models. So in the past few years, we have been looking into this space, and more specifically, how can we create those programming languages and synthesis flows targeting those highly diverse hardware platforms that includes multi-core CPU or GPUs or even FPGAs. So I would say this part is the part that connects the application and hardware platform is very, very critical. And we have done some work in this domain, and each part of those compilation synthesis is not straightforward. So each platform has their own characteristics, have their own advantages. So it's very not very straightforward to create a very powerful compiler. We have done some work that generates efficient CUDA code for GPU. We have done work for FPGA, which is the PyLog project I will talk about today. And we've done some work on for emerging architectures like ReRAM accelerators. And on top of that, those compilers not only help us to get efficient hardware and efficient accelerator code, but also it kind of provide us a layer, an abstraction layer to into the hardware world. So if we stand on top of those abstraction layer, what we can see is those high-level operators that is provided by those compiler. So that also means on top of that, we can do design space exploration easier. So on top of the compiler, we are able to do design space easier and more efficient. So we have some recent work that look into that space. So today I will focus on the PyLog part, and it's a Python to FPGA accelerator synthesis flow. So just let's take a closer look into the FPGA design flow. So traditionally, people have been using circuit design languages and design tools to describe their hardware. So the hardware abstraction level in that space is a very low level, I would say. So using Verilog, VHDL, and the other hardware description languages to describe hardware. But at the same time, application side, people are using higher and higher level of language to develop their applications. So previously people use C heavily, but nowadays as a performance of processor increase, many applications can tolerate the performance of programming languages like Python, or even Haskell or Scala, those higher level programming languages. But the result is that the abstraction of software becomes higher and higher. And that also means the gap between the hardware abstraction and software abstraction is become more and more huge. So that means and also another thing to point out is that those software developed in high-level abstractions are typically the applications that require hardware acceleration. Because at the beginning, people may use those scripts to prototype some algorithm, but later on they want to deploy those algorithms in scale, and then they hope to leverage the processing power of underlying hardware accelerators. So PyLog is created to bridge this gap. And we pick Python because Python is getting more and more popular. Many applications, especially those data analytics, deep learning applications that are developed in Python. And many frameworks are created with Python. And many of those applications are the application that needs hardware acceleration. So we start with Python. So for FPGA programming, at the very beginning, people use hardware description language to generate FPGA design. Later on, people create high-level synthesis floats. So more specifically, here I'm showing C-based high-level synthesis flow. So basically, people can simply code in C and then add pragmas. So add those compiler derivatives to tell compiler how to optimize the code. And then high-level synthesis flow will take over and generates hardware. So in this approach, it indeed increase the productivity of hardware development. It requires few lines of code. It enables easier system integration, and it allows us to easily port our design into different target platforms. It enables easier design space search, so we can optimize at a very high level, at C level, and we can explore more alternative designs. And I mentioned easier mitigation, and I would say those are kind of the benefits of using high-level abstraction or using C language. So people will focus more on the algorithm specifications here. But at the same time, we noticed some drawbacks. So first of all, C is designed to describe sequential execution for CPU, and it's actually not very convenient and to describe concurrency. And FPGA, we know it is very good at fine-grained pipelining and parallelism. So there's some inconsistencies between C syntax and the concurrency we want to express for FPGA. Also, because we are using those high-level synthesis tools are using C, and the compiler tends to be more conservative because it's not trivial for compiler to figure out the data dependencies between those data elements in the code. And also, because of the previous two aspects, in order to create those highly performant code, people will need to add more pragmas and more careful and requires careful tuning, and that will quickly grow the lines of code for high-level synthesis C. So then again, it becomes not that efficient to program in this kind of abstraction. So this is telling us that we need languages for with high-level operators. So those high-level operators will only describe the algorithm, but it's not that specific enough regarding the implementation. So for example, array operations. So think about array vector add. Those high-level operators will only say vector add, but it doesn't specify the order of adds for the elements. But if we are using C, we will need to write a for loop, and for loop implies the order of the add for the elements. So with those high-level operators, the compiler will have more information about the code, about the computation, and has less constraints about when you start to do the optimization for the code, right? So if we look at the limitation of HLC, we realize that the compiler needs to incorporate more powerful optimizations, but more powerful optimization needs more insight about the code. So at the end, that means we need high-level programming flow. So that's why we create PyLog, and we build PyLog on top of high-level synthesis flow, C-based high-level synthesis flow. So PyLog code will basically take Python program, analysis, do analysis, optimization, and then generate optimized HLC code. So I'll go into the steps of the PyLog flow. So here, let's take a very high-level overview of the complete PyLog flow. So here we have an example PyLog program, and it's in Python syntax basically. So we can see here we have a Python function, and it's decorated by PyLog. So we provide the PyLog compiler in the format of Python decorator. So Python decorator is a special type of Python function, and it takes another Python function as input. So in this case, it takes the add function as input. So basically, the PyLog decorator takes the add function as input, read the code, and basically it analyzes the code, do optimization, do codegen, and then generates the efficient HLC code. So only this part, which is the function that decorated with PyLog, will be compiled by PyLog compiler, but the rest part of the whole code will be interpreted by standard Python interpreter. So the rest of the code it's can so basically support any Python features, any Python libraries that you like to use. So and also the rest of the code will become the host code, or the CPU code. So only this part will become the accelerator. The rest will be the host code. So so basically, in the synthesis parts, PyLog code generator will take this part of a decorated PyLog function or PyLog kernel, do analysis, do type inference, do optimization, and finally generate code. And the code is optimized with pragma kind of C code. And then PyLog has a system generator that generates Tcode scripts, pack the generated HLC code into FPGA IP, integrate the IP with the other system components, and finally produce the complete working system. And that is the complete FPGA system. And after the synthesis, PyLog has a runtime part that basically take the generated FPGA bitstream, program the FPGA, allocate memory accordingly, and then populate the memory, start the accelerator, and then collect result that is produced by the accelerator. So at the end, after the synthesis, when the user want to deploy their accelerator, they simply call their PyLog code with standard Python interpreter, so Python 3, vec add or py, and then they will get the results. So so basically all the deployment detail is hidden behind the PyLog flow. So okay, user won't be aware. Yes.
Yeah, I have a question. So it's very cool. Yeah. So because I'm familiar with PyRTL and PyMetal, that they do Python, but here it's different in the sense that you are first difference, correct me if I'm wrong, is that you generate HLS C. So you generate a C that is friendly. What do you run out of that? So it's like something like a Mentor or Catapult or something like that. What do you run to?
We target Xilinx boards, so we use Xilinx Vivado high-level synthesis to run the synthesis. Yeah.
And then the other thing that is interesting is that the same code, it will allocate the memory and more the managed, so you can talk between the RTL generated and the non-RTL generated. That's also a significant difference with these other flows.
Yes.
There is any other difference with the PyRTL, PyMetal, and those ones that I'm missing? Or
right, so
those are significant, but what else is there?
Yeah, so I think the kind of the design level are pretty different. So for PyMetal, for PyRTL, I would say they are more similar to hardware distribution languages. So the code in PyLog or PyRTL, the code is describing hardware directly. So it's more specifically, it's a register transfer level. But here we are operating on data objects. So here, for example, A and B here, they are arrays, they are NumPy arrays. So the code is operating on data objects, and it's kind of platform independent. So the data object may become a piece of data sit in local memory. It may correspond to data in global memory. It can become implemented with registers. So those are all possible. So after synthesis, but when people program in PyLog, they are not aware of those hardware details. So they only know we have data objects. We manipulate those data objects, and that's it.
Okay, and there is also a question on the Q&A. I don't know if you see it. You want to answer?
Yeah. So the question is, so what kinds of Python syntax are allowed in the illustrator? And I can imagine a lot of parts of the language we typically use in normal program is expressible in InterC. Yes. So very good question. So indeed, for high-level synthesis C, there are many limitations, and same here. So for PyLog, even though we are writing in Python syntax, there are still many limitations. So we were trying to cover those most frequently used Python syntax, but still there are many we haven't supported yet. So for example, we support list, we support NumPy arrays, array allocation. Well, it's not exactly allocation, but it's a fixed sized array allocation. So during compile time, we require that the size of the array should be fixed, because we require that for high-level synthesis. We don't support dictionary, for example. We don't have classes. We don't have object-oriented programming still. So still, I would say it's still a very small subset of a Python code. But we are trying to add more support into that, especially add more support to connect to external HOSC libraries. So we hope that with those kind of external interface support, we'll be able to connect to those pre-built, highly efficient HOS libraries. Yeah. Okay, so is there any other questions?
No, go ahead.
Okay,
thank you.
So thanks. So I'll continue. Yeah, so next, I will walk through some of the features in PyLog. So basically, I mentioned that are high-level operators. So the high-level operators, I mean operators like map. So we know Python has a map operator, not only map, but also those NumPy style array operations. For example, elements multiplication. Element-wise multiplication for vectors for NumPy arrays. So basically, those are operators I mentioned. They only specify the algorithm, but not the order of applying the specific operation. So then the compiler has the freedom, has the flexibility in producing nested for loops. So essentially, those high-level operators will correspond to a groups or some groups of nested for loops. And there are many ways to generate these kind of for loops, right? So there are many design choices. And depending on different contexts or the different hardware platform, there could be large FPGA boards, there could be small FPGA boards. Some operators may be more critical than the others. So depending on those contexts, the optimal version of the HOS code could be very different. So PyLog internally will choose the optimal implementation given those constraints. And then not only the high-level operators, we also support those lower level, more fundamental Python statements, those control statements like for loop, like if else. And then for those lower level operations, we allow people to customize them. So for example, we have the attributes for list range and say, okay, we like to pipeline this. And then the compiler will generate those C code with corresponding HOS derivatives. So basically, this allows the programmer to customize their hardware. So if they choose to go around the optimization provided by PyLog, they can fully customize their design in this way. Also, there are APIs that generates the fixed point data type, which is very helpful in FPGA designs. And I mentioned that so basically accelerator and host will be programming in the same language, same syntax basically. So they have in this way we allow to have a closer kind of interaction between the accelerator and host. So the interface is essentially those NumPy arrays. So for the top function, those arguments are basically NumPy arrays. And the next feature I will mention type inference and type checking. So we know that Python is dynamic typed, and there's no hints on type basically for compiler. So we have a built-in type inference and checking engine inside PyLog. And we are able to do that because the inputs for the top function are NumPy arrays, which carries the type and shape information. So basically what the type engine does is it starts with those inputs for the top function, which has a no type and shape, and then it propagate according to the type inference rules. And gradually we get the information for all the code objects within PyLog code. And also, just to mention, this is possible for HOS flow because for HOS, at the same time, we have those constraints. For example, we cannot do dynamic allocation because everything, within the top function, we cannot do dynamic allocation because everything needs to be determined during compile time in order to be accepted by high-level census flow. So with those constraints, we'll be able to know all the type and shape information for all the code objects within the PyLog kernel. Yeah, so based on those information, we are able to do code gen. We know what kind of for loop, what are the boundaries to generate. Yeah, so I have some slides to go through the details of PyLog flow, but I think I will quickly go through this and then jump to the optimization result part. So the C code generation is the most critical and most important part in PyLog. And there are a few steps. So basically, first of all, we use Python AST library to parse the PyLog code. This is because PyLog code has the same syntax as the standard Python. So we are able to do that. So basically we got the PyLog AST by using Python AST package. And then we kind of aggregate the nodes within Python AST into those high-level operators. So for example, I mentioned map operator. So we will discover those map node in the code and aggregate those into a single node. So here we may be able to see those nodes, for example, PL map, PyLog map, PyLog dot, and some other high-level operators. So this is visualized in a tree format. So basically, those are high-level operators, and those are the place that PyLog can do optimization. And then on top of this, we traverse this tree and do type inference. So just to one thing to notice that for the same the code objects with same name, they can have a different type and shape at different places in the code. And basically we traverse and annotate the tree with type and shape information. And then we start to do optimization. So optimization is basically a place that we implement those high-level operators with lower-level controls or lower-level for loops, basically, more specifically. So we use for loops. We put together loops to implement the functionality of those high-level operators. And the way we put together those for loops is very critical. And PyLog will determine the best way to put together those for loops. Yeah, so after the optimization, what we have is lower level IR. And it's basically, there's no longer those high-level map operator or vector operations. And all those operators are basically compatible with Python, standard Python. So after that, we do codegen. So we generate CAST, and then we use an external library to generate the C code from the CAST. So that's the complete flow of the code generator inside PyLog. And as I mentioned, after that, it's the system generation and then runtime part that we already mentioned. Yeah, and another thing to mention is PyLog. We provide PyLog as a Python decorator, and we also provide some actual arguments to be passed along with to that PyLog decorator. So this PyLog decorator can accept actual arguments, for example, compilation mode, for example, target FPGA boards or frequency. So for PyLog, there are several modes, and here I'm list 4 frequently used mode. So for example, C generation, hardware generation, deployment, deploy mode. So that will basically program FPGA and run FPGA. Also, there's a mode called PySim. So basically, PySim will simulate PyLog code with standard Python interpreter. So this is very helpful for people to debug their code with standard Python interpreter. Yeah, and next, I mentioned the high-level operators. So we have those vector operators, we have map, and one thing to point out is that for those high-level operators, the same expression may have a different meaning depending on the context, depending on the type or even the shape of those code objects. So for example, C equal to A plus B. So A and B could be scalar, could be array, may have the same shape, may have different shape. So depending on all those conditions, they have different meaning. So that's why the type inference is very important. So based on the result of the inference, the code generator will generate the corresponding code. I mentioned the map operator. So one thing that we enhance the standard Python map is that we allowed this lambda function here to access not only the current element but also the neighbor elements. So we allowed it to access those elements in the same array, but with some offsets. So for example, the standard Python map will basically repeatedly apply some operation f to, for example, each of the element here. But here we allowed the PyLog map to access some of the neighbor elements. So well, with this offsets, the program is able to access, for example, the element here, and so on. So with this extension, we can describe much more applications or computing patterns with this map operation. So for example, 1D convolution, we can describe, for example, 2D convolution, for example, stencil code, or even high dimension stencil, and also image filter, image pipelines, and so on. So those can all be described with this enhanced map operation. And some other examples, for example, the inner product can also be described with dot product. And some squared metric multiplication can be described by combining the map and dot operation. So there are many other examples that can be described with the map operation. And so as long as the code use the map or vector operations and or other high-level operations, those places are the place that the compiler has the opportunity to explore the design space and optimize. So for the optimizer, basically, there are two things that the optimizer needs to do. So first of all, it's generating a loop nest. So there are many ways to generate the loop nest that has the same functionality as the original high-level operator. So that's one dimension. Another dimension is you need to insert the pragmas. So you need to insert the HOS pragmas into those generated loop nests. So basically, the way we did that is we had a at the PyLog IR level, we use the schedules, which are a sequence of loop transformations. And those transformations are transformations that are going to be applied to planned for loop. So in this way, we construct the design space of all those candidate loop nests. So for plan for loop, if we apply interchange and then tiling, we get one version of for loop. If we instead do tiling only, we have another version. So this is the way we describe the design space, and we generate basically all the candidate designs in the abstract design space. So, and then on top of that, we explore the design space. So here I'm showing one example. So there are many design candidates, and we kind of profile those candidates with our performance and latency model, and we figure out the design points that falls at the prefill curve of among all those design points. So prefill curve is basically the curve that consists of the points that given a specific resource or utilization, it will generate the best latency, will generate the shortest latency among all the other design points. So so those design points are the representative optimal design points for a specific operation. And we can see in different contexts, sometimes we want an operator that has a smaller resource utilization, maybe longer latency, but some other cases we need very efficient, very short latency operation, but that will consume more resource. So there are latency resource trade-off here. Given that so making a decision really depends on the context. So after this, after we get a prefill curve, we then move to the global optimization. So global means it's optimization done for all those high-level operators inside the PyLog code. So we're doing this optimization using integer linear programming. solver. So we basically formulate this problem into an integer linear programming problem, or ILP problem, and use and call the external ILP solver to solve this problem. So basically, for each operator, there are multiple candidates, and for each candidate, they have specific resource utilization and latency number. So based on those information, we feed those information into the solver, and the solver figure out what, given the constraint of a resource, what is the shortest achievable latency for all those different versions. And this formulation can also be described the interface between CPU and FPGA even. So for example, the data copy between CPU and FPGA. We just need to know which version are FPGA versions and which version are CPU versions. And then we can characterize the data copy using those formula. And so basically, for PyLog, we are able to support both SoCs, which has more power constraints, as well as those high-end FPGAs that is PCIe based. So for example, FPGAs in Amazon AWS instances, those are latest Xilinx Avio FPGAs. And we, in the backend, we use Vivado Hello synthesis and Vitis to generate those FPGA accelerators. For the runtime, we use Pink. So Xilinx Pink is a very, very helpful and flexible runtime library. So it basically provides those lower level API to program FPGA to kind of create shared memory space to copy data, and then PyLog will call those APIs to construct to build the environment for FPGA and invoke FPGA. And we can easily target different FPGA by changing the target board, or change between synthesis and deployment mode using the mode argument in PyLog. So if we compare the PyLog with more traditional HOS flow, we can see we are able to achieve quite significant reduction in terms of lines of code compared to HOSC code. So we're able to achieve around 70% of reduction against the traditional HOSC code. So that's also a recent work called heterogeneous. It's also a Python-based FPGA synthesis work. And so there are some difference between this and PyLog. So PyLog is more high-level synthesis flow. So it synthesizes the Python code directly. Heterogeneous takes the approach of that is more similar to Halide, and it constructs the computational graph during the runtime, and then generate code out from the runtime. So we are able to achieve similar lines of code, or even less lines of code compared to heterogeneous. And if we compare the accelerator performance, we are able to achieve speed up compared to those highly optimized CPU code, single thread CPU code, and the speed up. The average speed up is around 3 times compared to optimized CPU code. And compared to heterogeneous, we are able to get some speed up as well. We are continuing to optimize our design, and we are adding more benchmarks into the space. So before I move on to next slide, is there any questions so far?
No questions from my side. Very cool. Yes, curious, the hetero-CL, does it generate, I'm not so familiar with it. Does it generate a C code and then it goes to the Xilinx XL2, HLS?
Yes, that's correct. Yes. So the backend of heterogeneous is also Xilinx tool chains. So Vivado HOS C-based synthesis.
And then the reason for the speed up is because of the linear optimization on the kernel, the integer.
Right. So Yeah, so for heterogeneous, there's no so the optimizations needs to be specified by programmer. So there's no implicit optimization inside the flow.
Okay.
Yeah.
I think it's a similar question what Thomas was asking. Is like if the backend is the same, why do they have different speed up? It's one of the questions that someone typed, but it's what you just mentioned. Is that one is custom directives, the other one you do a search space for the directives?
Yes, exactly. Yeah.
So I have a question kind of dovetailing on that about optimizations. Are your heuristics in ILP sufficient to predict performance, or do you find you need to maybe synthesize multiple designs and test them out?
Yeah, good question. So at that stage, we actually do not test the I mean within PyLog, we do not test the synthesizable whether it's synthesizable or not inside PyLog. So we simply generate candidates and run through the flow after we generated the actual code. But when we do the space exploration, we do have that check inside PyLog. But I mean, because we are exploring those high-level operators, and those high-level operators are very well defined, has very regular, well-defined pattern. So we know what is exactly happening for a given high-level operator. So we generate the loops.
So you're able to estimate the frequency when you are doing those transformations? Because one thing is the number of cycles it's going to take you, but another is the frequency target you're going to have the FPGA. So when you are doing those transformations, are you able to estimate the frequency?
Frequency-wise, we are not able to estimate, but the estimation is a very high level, very rough estimation in terms of resource and latency. Yeah.
Okay, so just curious, when you are reporting those numbers, I'm assuming that you take into account the frequency, and that's the time.
Yes.
The execution time, no?
Yes, yes. So when we at the last stage, we generate accelerators, we push for the higher frequency, as high as possible frequency. Yeah. Okay. Yeah. Thanks for the questions. So let me continue. So I have a few more slides, and so one thing I want to mention is so recently we introduced the flow to one graduate level course, SOC design, and there are still 2 students used PyLog to build their final project, and it's a verification infrastructure. And I feel it's pretty interesting. So I mentioned code generation from PyLog to high-level-C. So the question people may ask is that how to check whether the generated C code is correct or not. So then there is a problem of a testing and verification between verify the PyLog code and the generated C code. So the 2 students, Ajena and Chris, so they build a completed automated flow to generate test vectors and fit into PyLog code, and at the same time onto the generated C code, and run tests and get a report of a coverage of the testing, and then check all the possible potential bugs. And here let me show this. So here is a very quick, a short video that shows the steps of running the flow. So basically, after the verification flow is run, at the end, it will generate a report that basically is saying the coverage of this test. So for those test vectors, we know some, depending on the test vectors, some part of the code may be run, some part may not be run. So this report basically saying what's the percentage of the code that has been run during this set of test vectors. So and notice that here we have a report not only for the test program itself, the benchmark application program itself, but also we have the test result for the PyLog code. So I feel it's pretty interesting. So at the same time, we are not only testing the application code, but also we are testing PyLog itself. So we get to know whether there are potential bugs or whether we have a good set of testing benchmarks or not. So at the end, this is a report saying which lines of code is run during the test. Yeah, so in this case, it's 100% coverage for this vec-add example. And then next slide. So we have some ideas about the next steps of PyLog. So one direction we're exploring is can we use PyLog to program heterogeneous systems in a heterogeneous environment? So more specifically, the first step, can we program not only one single FPGA, but one single FPGA, but multiple IPs, or even CPU plus FPGA, or multiple FPGAs, or even FPGAs across nodes. So how can we scale out? So I think that's a very interesting question. And the good thing is that PyLog provides those high-level operations and interface, and if we complete this, then it'll be great. It will be greatly improve the programming efficiency for those heterogeneous systems. And here I'm showing one very brief example. So let's say there are multiple PyLog kernels decorated by PyLog decorator. Then there could be a high-level Python code, Python function that combines those individual kernels, and we are able to specify the connection between those kernels within the high-level function, Python function. So everything will become can be done at a higher level, and those kernels can correspond to different devices in the heterogeneous system. So I think there are many interesting research questions to ask, like how to efficiently map those kernels onto the best target device, how to optimize the interconnection between those, how to enable the collaboration between multiple accelerators, for example. So those are very interesting questions to ask. Yeah, to summarize, this is a Python-based high-level synthesis flow, and we have a Python-compatible syntax kind of language at the front end, and the compiler take over more optimizations in this flow. So the compiler try to explore the design space and figure out the best design. And then PyLog has the supporting flow that can generate the complete hardware system, can run the hardware accelerator. And in the future, we'd like to explore more opportunities in terms of the type of the accelerator, as well as the type of system that has heterogeneous devices. Yeah, and this concludes my talk. So I'm happy to take questions.
So thank you very much. Very impressive work.
Thank you.
Like clapping virtually. One question that I have, I've been looking through what you were talking, I couldn't resist to look at GitHub. I couldn't find it. Have you released the code for this?
Oh yes, so we are so recently we are actively working on this, and we are pushing for the open source of this whole project. And our target will be around early March, sometime around that. So we are cleaning up our code base, and we will open source this very soon.
Okay.
So I had one question. This is a really exciting work, and I appreciate how you sketched out future work of scaling to multiple devices, heterogeneity. Is there any interest in going the other direction, going even higher level? Where right now, PyLog seems to be quite general purpose. Could you imagine maybe making it more specialized for a certain application domain and providing more Python data structures that are more natural for that domain?
Yeah. Thanks for the question. Yeah, this is very interesting. So, actually, at the very beginning, the reason why we choose to use Python, besides the reason I gave at the beginning, the other reason is that Python supports both like more traditional style of programming, like sequential imperative programming, but also it supports functional style of programming. So that's pretty interesting. So so for example, it let's say functions as objects, and then a function can be used as an argument to the other function. And in that case, we can have like partial functions, and that potentially can simplify the description of a design space. So that's something that we may need to think more in the future, and that is super exciting. And also, there are previous work that use functional programming language to generate hardware, and in some cases, those functional programming languages are very hardware friendly. Actually, they can describe pipelining, shift registers, for example, in a very natural way. So there are many lessons we can learn from there. Yeah, and this also reminds me something. So recently, we also have a kind of a sub-project that is about adding some support in PyLog that allows people to describe the hardware structure directly instead of all the algorithm specification, but also some structures. So for example, reduction tree. And reduction tree is one example that's not that easy to describe in high-level sense C or in Python. So we are trying to introduce some APIs, some abstraction, so that people can easily describe those structures. Yeah.
Great. One other related question, I think you may have already partially answered this when you described the course project did the correctness testing. One issue that comes up when you make source-to-source compilers, transpilers, whatever you want to call them, like you're doing here, is the user writes in one language, and it gets passed in another language to a tool, which gets passed in another language to a tool, and far down the stack, something else happens. And they want to correlate the two. They want to debug it. They want to see your resources went. So do you have any support for that to help users understand how their PyLog code gets turned into HLS or Verilog or something?
Yeah, that's a very good point. So at this point, unfortunately, we don't have that support yet. But that is indeed a very important thing, very important feature to support. And I can see with the PyLog flow, we should be able to support that, and I think that's definitely doable. And because we are basically the transformation that are mainly done for those high-level operators, so we're able to correspond to the loops in the final codegen back to the operator inside the original PyLog code. And so yeah, so the idea will be we will encourage the user to use more of those operators, and so that the compiler can have a more flexibility, more freedom to explore space. And at the same time, debugging for the user could be one problem. So unless we guarantee that our transformations are 100% correct, or there could be some tricky part in telling user. So we may be able to tell, okay, this map has some problem, but whether or not the user may be able to is able to figure out how to change the code is another question. So we need to think more about this question. Yeah, this is a very critical question. Yeah.
So are we connected with this, with the debugging? So I'm assuming that you can write some PyLog code that is not valid, like maybe you can do a combinational loop or something like that for running Is it possible to execute the PyLog code on the Python base so that you don't have to deploy to an FPGA, or do you always have to deploy to the FPGA for testing?
We have PySim mode that runs the PyLog code with standard Python interpreter. So it's this mode. So if we turned the mode into this, it will be interpreted by standard Python interpreter. Yeah.
And if you have, just as an example, you have something like a combinational loop, what will happen if I encode like a combinational loop in the PyLog? It will flag as an error. It will be, or it's not possible to encode something like a combinational loop.
So, so I mean, so you mean combinational loop?
Yeah, imagine that I mistyped my PyLog. Yes, because I don't know PyLog, so I'm a novice, and I create a combinational loop. How will that kind of error manifest? Just to have an idea of what will happen when you do mistakes.
So so I didn't quite get what does it mean by combinational loop?
Well, maybe you cannot specify. I'm not so sure with the syntax, but if I were specifying gates, I can specify one gate and another, and then the last gate fits the first gate, and there is no flop in between, so that it's a combinational loop there.
I see. So I see. So so actually, the Python code here, it's very high level. It's all about data objects. So it's hardware independent. So basically, it's a high level abstraction. So basically, that's no direct way to create a combinational lock.
Okay.
So
some of those programs you don't have them. Okay.
Right. So this is one difference between PyLog flow and PyMetal or PyRTL flow.
Yeah, Jose, I can't imagine how that would look in the Python AST for a combination loop, right? Because you'd imagine you assign one variable, but then when you assign a second variable, it's going to reference the most recent write, not the original one. You can't, because you have ordering semantics in the language originally in Python. I don't know how to get the circular dependency there.
Yeah, if they have a connect, the concept of connect or something like that, they can have it. If they do just assignments, no. I don't know the syntax. Maybe.
So basically, because we are using high-level synthesis as a backend, so if the code passed the PyLog codegen, and it will then be interpreted by, synthesized by high-level synthesis flow. So I think in that case, I guess most likely the error will be thrown out by the HLS synthesis flow.
Okay.
Yeah. We don't have that many checking in PyLog at this point. We check the types. We check the types whether types and shape are compatible given the definition of the operators. But for the type of bug that you mentioned, I don't think at this point we can detect that.
Great. More questions from the students, maybe?
Looks like there is no more questions. So let's thank the speaker. Thank you for coming.
Thanks a lot, everyone.
Very interesting work. We'll check when you release open source. Nice work.
Thanks. So if anyone has further questions, so feel free to email me. I have my email here. And yeah, so we would like to learn more about the source, the comments, anything about the work. Yeah, thanks a lot.
Thank you.
Thanks.
Great
Bye.
talk. Thank you.
Thanks.